Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2, with the course code PHY 222, we are at the lecture number 4, and the topic is Fourier Coefficients. In today's lecture, I will explain that how a periodic function can be expanded into Fourier series, and then the coefficient of each term can be calculated. So first I will give you the derivation of the general formulae for the coefficients, and then with the help of an example I will tell you that how we can calculate these coefficients. So let's start, and first of all we will talk about two things before starting the procedure, and that is the expansion of the periodic function and the period of that periodic function. So we will expand any given function in terms of series of sines and cosines. So we have chosen these sines and cosines because these are periodic functions, and these are convenient periodic functions. So therefore we will expand any function given to us first into the sines and cosines. These are the trigonometric functions, and then the other thing is about the period of these sines and cosines. In this lecture we will select the period to be 2 pi. Now since these sines and cosines can have shorter periods as well, namely that is 2 pi over n, so it's true that we can also have these periods, but important thing is that we are interested over here only in the intervals of 2 pi, these intervals of 2 pi. So later then the sine and cosines with these smaller periods can have similar general formulas for the coefficients. So these are the two things which we have to know in advance. The first thing is that we are going to expand the function in terms of sines and cosines, and secondly that we are talking about only the periods 2 pi. So now let's start the procedure, and first of all expand our given function, any general function, into which has a period of 2 pi, into a series of sines and cosines. So this is the series and how the expansion looks like. So let's understand each and every term over here, written over here. So on the left hand side we have this general function expanded, and this is equal to the first term you can see over here is 1 over 2 a naught, and this a naught here I have put n is equal to 0. So this first term actually corresponds to n is equal to 0 case, and this 1 over 2 cofactor is actually a convenient choice. At the end you will see that if we have not chosen this 1 over this cofactor equal to 1 over 2, then we could have an ugly term there. So in order to avoid this we have in advance made this convenient choice of 1 over 2. Then the next term in the series is actually the cos term, and since n is equal to 1 over here, so we get a1 and cos 1x. So this is the second term in the expansion, and similarly the third term where n is equal to 2, we will get a2 coefficient and then cos 2x, and then similarly a3 cos 3x, and so on. So there will be a general term a n cos nx at the end of the expansion of this cos series, and then we will start the sine series where we will have the first coefficient b1. Here n is equal to 1 for this sine 1, so we will have b1 sine 1x, and then we will have b2 sine 2x in the second term where n is equal to 2, and then b3 sine 3x, and so on, and the general term would be bn sine nx. So this was the expansion of this function into sines and cosine series. Now our task is to derive the general formula for these coefficients, that is from a naught, a1, a2 to an, and then b1, b2, b3 to bn. But before going on into the derivation of these Fourier coefficients, these are called Fourier coefficients. So before going into the derivation of the Fourier coefficients, there is another important point to note, and which we have already done, is the average values of these functions, because we will use them in the derivation. Therefore it's important that we know what are the average values of particular functions we will be using here. So some of these average values I give you is this is the first one, where you see that sine mx and cos nx average value in this interval is equal to 0. I will also show you how to prove this. Some of them we have already proven, but for example for cos square and cos nx we have proven, but I will give you a general recipe for proving these average values. But at the moment, just note down that sine mx cos nx average value is equal to 0 over this interval, and the next important thing you want to know is sine mx and sine nx. So here you note that there is one is sine and another is cos. This kind of mixed term, average value, which is equal to 0. So we are going to have mixed terms in deriving the coefficients. And then we have sine mx and sine nx. This is only the pure sine term, and its values are different for different values of m and n. So if m and n are not equal, then it's 0. If they are equal but equal to 0, it's 1 by 2. And if they are equal and equal to 0, then it's 0. And similarly for the other average value, where we can have pure cos terms, for example cos mx and cos nx. This is again if m and n not equal to 0 is 0, and m and n equal and equal to 0 1 by 2, and m and equal and equal to 0 is equal to 1. So these are the average values. Now I give you the general recipe that how you can prove that these general values are true. For this there are many methods, but one of them is to use the complex notations. So in the complex notation, you know that this sine and cos can be written like this. And now once we have put these sines and cos into a complex form, then what we have to do is to multiply them all. For example, first term will get multiplied with the first, and second with the second, and so on, first with the third, and so on. And what we see over here is, because in sine exponential notation, complex notation, we have minus, and in the cos we have plus. Because of this we will get the cross terms or the mixed terms cancel out, and we will be left with only single terms or pure terms, you can say. And these pure terms, for example, are the form of e raised to power I kx, and this integral is now very simple to calculate, and this is equal to I kx by I k, going from minus pi to plus pi. And if you put in these limits over here, you will see this is equal to 0. So we have ik pi is equal to minus ik pi and is equal to 0. So in this way you can calculate all the average values. So what you need to do is to put their exponential forms, and then from these exponential forms these integrals, class terms goes away, and the mixed terms goes away, and these integrals are very simply calculated. Okay, so after having said this, now we go towards real calculation or derivation of the formulas for the coefficients. So first we start with the first coefficient a naught, and what we do is to this a naught coefficient, we expand the function, and the expansion, this whole expansion, after this whole expansion we want to find out the average value of each term. So this first term and second and third, each term. And the interesting thing is that if you calculate the average value of all these terms, then only first term survives, that is encircled, and all other terms are equal to 0. So if because of these average value formula I have shown you on the last slide, so this term will be equal to 0, because its average value is 0, and the second will be equal to 0, and so on up till last term. All of the terms are equal to 0 except this first term, so only a naught survives. So from this term over here, we need to calculate this integral, and if we calculate this integral, then we get it equal to a naught, because this integral is Gaussian. It's very simple to calculate it. You already know its value. You put it over here and you get a naught, and then from the equating with the left hand side, the general formula for the a naught is 1 over pi minus pi to plus pi f of x. So we have derived the general formula for our first term, that is equal to a naught. So now move towards calculating our second term, that is second coefficient a1. In this case, now what we will do is to before calculating the average values of this series term by term, we will multiply with the cos x, and what it will do us for is that all the terms we multiply will get extra cos x term. Let's say on the left hand side we multiplied this fx with the cos of x, and then the first term got the cos of x, and the second term already had a cos of x, so then it will be cos square of x, and so on. And interesting point is that now only this term will survive and all other terms will go away. So when we will take the average value of this expansion term by term, so only this term will survive and all other are equal to 0. So this average value is 0, this average value is 0, and this average value is 0. So all of them are equal to 0 except this a1 term. And if we now calculate this a1 term and this integral, we get 2 pi, and which is equal to 1 over 2a1, and from here the general term for the a1 is 1 over pi minus pi 2 plus pi, and this is cos of x dx. So in this way now you might have learned that how we can calculate or derive the general formulas for the coefficients. So now for the next term, which is cos 2x, you know that you have to multiply with the cos 2x the whole series and take the average values, then only a2 term will survive, all other terms will go away, and we will get the a2. And similarly for the general formula for the coefficient an, we will do this procedure again and multiply by cos nx the whole series, and if we multiply the whole series with the cos nx, as you can see over here, then what will happen, that only this nth term will survive and all other terms will be equal to 0 when we take their average values, and the formula for this an term will be equal to this 1 over pi fx dx cos n of x. So this is the general formula, and you can have all these terms from here. For example, if you put n is equal to 0, you will get cos 0, it goes away, equal to 1, and then a1 will have cos x, and a2 is equal to cos 2x, and so on. So this is the general formula for the cos series coefficients, which we call a's, which we have derived by taking the average values of each term or in the expansion. And similarly, if we do repeat this procedure for the sine term, so the only term difference would be that now we will multiply each term with the sine 1x and sine 2x and sine 3x, and all other terms will go away, but when we take their average values, only particular that specific term will survive, and in this way we will get the coefficients formula. For example, I over here show you the general formula for the Bn, which will be equal to this. So in this first part of the lecture, I have shown you that how we can derive the formula for the coefficients in Fourier series for these Fourier coefficients. Now once we know this, that what are the general formula for the Fourier coefficients, then it is easy to apply to any explicit function. So now I give you an example where I will show to you that how this whole procedure can be applied to a particular function, a periodic function. So let's take a function in this diagram. This physically means could mean that it is some voltage, a periodic voltage, which have these periods, and we want to now calculate particular frequencies involved over here, and would like to see that which one is actually important. So this is just the diagrammatic representation, and we can put it into the mathematical form. For example, here you can see that in this interval it was equal to 0, this function in this diagram was equal to 0, and in this interval it was equal to 1. If you go back to this diagram, you can see that when it is equal to 0 and when it is equal to 1, from 0 to pi in this interval. But unless you sketch it, you won't see from this mathematical form that what are the real expansion of the function. So therefore it's important that when you have the mathematical form, then you also sketch the function in order to see the complete expansion. So now our task is to calculate for getting the expansion, to calculate the Fourier coefficients first. So since we know the formulas for the Fourier coefficients, and we also know the explicit form of the function, now it's important, it's now just about to put in the values and get the coefficients. For example, for the an coefficients, as you know, this integral can be split into two forms, two parts, and the second part, this part is survives, and then we can calculate the coefficient for n not equal to 0 and for n is equal to 0. So you know that what is the integral of cos, which is sine, and then you put the limits in there and you get 0. But if you have n is equal to 0, then you get equal to 1. So we get a naught now when n is equal to 0 equal to 1, and all other Fourier coefficients an are equal to 0, because we knew the general formula, we just calculated the integral, and from that integral we got the values a naught and an. Similarly, we can get the other coefficients, for example bn. Again we split the integral, and in this particular example, and then we calculate the integral of sine nx, which is equal to this, and then this you get this value. And now in order to get the complete expansion, what we have to do is to for a fully expanded function is to put in these all a values. This is the a naught, a1, a2, because the sine terms survived. So this is the complete expansion of that function, expanded, sketched into that diagram. So in this way you have seen that how we calculate the coefficients, and then we put into the expansion, and we get the exact value, explicit value of this function's expansion. Okay, these are the references which you can consult, and at the end I would like to summarize for you whatever we have learned in today's lecture. So in today's lecture was about a very important topic of Fourier coefficients. So when you have a periodic function, then you want to expand it into Fourier series, you can do that. And when you have this expansion, the problem is you will get with every term coefficient, unknown coefficient, and in order to get the explicit form, you need to calculate these coefficients. So today's in the first part of the lecture we have derived the general formulas for these coefficients, and because we expanded the function into sines and cosines, so we had coefficients of cosines, which we called a's, and coefficients of sines, which we called b's, and we derive the formula, the general formulas for the A's and B's, the Fourier coefficients. And then in the example I have shown you that any physically relevant function which was sketched into diagram, we were able to expand it and also calculate the Fourier coefficients, and at the end you can analyze this and know that which coefficients were important. For example, these coefficients these terms could correspond to the different frequencies. This function could be the voltage of some circuit, and then in that voltage you have different frequencies given by the different terms and different coefficients, and then you can analyze and know that which frequency was more important. So that could be the physical explanation or physical importance of the Fourier series. So I hope you understood the how to derive Fourier coefficients and how to calculate them. With this, I thank you all.